Hello everyone, welcome to the Industrial Robot Simulation and Programming Internship Program offered by iRobo Automation and in collaboration with VTU, and this is approved by VTU. So in this course, what are the topics you are going to learn that is given uh, in the modules wise it is given in the flyer, in the internship flyer. In this section, you are going to learn introduction to Webots, Webot software download and installation, creating your first project or first world in Webots, and after that we are going to design two-wheel differential drive robot, and after that we are going to use a Python controller. So for that we need to download Python 3.8 and installation of the Python is required. Okay, so after that we are going to execute this many projects. Okay, like from simple project to even AI voice commands also we can use it to control the robots which are built in Webots. Okay, so in this section mainly focused on two-wheel differential drive robot. In the next videos sections we are going to design the four-wheel differential drive robot also. Okay, so let us take the first one, that is introduction to Webots. We can say Webots, first of all, it's a very good software, and very important point is like it is open source robot simulation software, and there is no license cost. It's completely free, so that is a favorable condition for students. Okay, so this software is mainly used for modeling, programming and testing of robots in a virtual environment. Virtual environment, sometimes it is very realistic. Okay, real time factors, for example friction, gravity, these things are added to the simulation, so that it is very simulation is very realistic in sometimes. Okay, in that way it is very good software. It is going to give the results, so it can be used for prototype purpose, development of prototypes. And this software is mainly used for students, hobbyists, researchers. Okay, even industry also in the development process, for example prototype development can be used. It's a very good software. Okay, next question is like, why Webots? So first of all, Webots as a 3D robot simulator. Okay, and that is the one thing, and multiple robot types we can develop and simulate. For example, differential drive robots, humanoid robots, drones, robotic arms. Robotic arms, there is industrial applications. Even differential drive also industrial application, but that comes under mobile robots. Robotic arms, industrial application, for example welding, painting. So these are the applications. Even drones also considered as a robot, and that is a flying robot, you can say. Humanoids robots are also can be developed and simulated, and then we can go for actual production. And realistic physics engine, that is open dynamics engine is there. So as I mentioned earlier, we can give real friction, gravity, so that simulation will be very realistic. And more important is it supports multi-language. That means controller can be C based, C++ based, Python based, Java based, MATLAB, ROS integration is also possible. There's a very advanced robot operating system can be used. So robot becomes intelligent, autonomous. Okay. So in this video section, we are going to cover Python. For C controller and C++ controller, other video links will be shared to you. So, okay, so we are going to do C, C++, Python, mainly focusing on C and Python. If possible, C++ also will be covered. Okay. Next is like question is why we use Webots. It's a safe environment for testing robots without hardware. So that means it is very ideal condition for development of prototypes. Cost can be saved, time can be saved. So that is called the rapid prototyping, and debugging is possible. That means code also you can check it in the software before actually implementing into the real robots. Okay, and supports sensors, actuators, complex robot interactions. For example, AI with robotics. Okay, so that is also possible. In this section, we are going to demonstrate AI voice and controlled robots are also can be demonstrated. And mainly it is great for education, research, even competitions can be held using this software because it's free of cost. And Webots interface overview means this is that means for demonstration I'm going to show you. There will be 4 main sections will be there. This one, text editor. Okay, we can see here important sections are, one is scene tree. In the left hand side you can see that there is a scene tree. Okay, in scene tree what are the nodes are there, proton nodes are there, base nodes are there. So everything will be listed in the scene tree. Okay, so that is in the left hand side, and in the center that is a space for simulation, and the right hand side you can see it's a text editor. Okay, text editor is here, it is nothing but a controller. So text file acts like a controller here. So here we are using Python, so that is why the controller ends with .py. Okay, and in the console section shows that what is going on, like what are the errors are there. So all these things it is there in the console section. Okay, so right now there is a robot. Just I'll show already program, everything is ready. So what I'll do is I will going to show how it is going to work. This is actually a voice enabled robot. Even with obstacle avoidance also, program is also there. For example, forward, and that means we should run the robot first of all. Forward, see it is moving forward. Obstacle avoidance program is also there, so it is detected the wall as obstacle and it is stopping. Backward, stop, left, right, stop, forward, stop. Okay, so here we are going to develop this means complete simulation, that is first designing of a two-wheel differential drive robot, and then later on development of code, and then integration of controller to the robot. So this will do in the later section. Here important section you need to understand, there are 4 sections are there: scene tree, then simulation area, then text editor, then console. Okay, so now that is a demo. Even pre-built robot is also there. So that means this is a what we develop, but we can also use the predefined robots also there that we call as protonodes. Okay, you can take a new world and go to file. So there, open sample world. So there are robots are there, like different companies like ABB robot is there, Festo is there. So like that, Robotis is there, Okay, anyone you can open it. iRobot is there. So you can take ABB. So proto nodes means already robots are ready. You can directly use it. See here, if you play, okay, so this is a ready-made robots are there, so that we called as a proto nodes. Okay, so this is just a demo. I'm going to close this. Fine. Next is we understood the main sections of Webots. Okay. Key features of Webots. We can say that you have observed that there are different types of robot controllers are there. Okay. 5 different languages: C, C++, Python. Then many programming languages are there. Okay. So that is advantages. Single software offering multiple languages. Okay, even variety of sensors and actuators are available. Gravity, collisions, frictions can be added, so that becomes very realistic simulations. We can import 3D models. That I will show you in the next section. If design is ready, we can import. For example, we can use a 3D software to design the models, and those models we can import to the Webots and then create simulations. That is also possible. So we can run simulations in faster, slower for different analysis. So that is advantage. When it comes to applications, mainly education, so currently we are also using for education. So teaching robotics and control systems, research, testing autonomous navigation algorithm, for example, line following robot or wall obstacle avoidance robot. Okay, so there are many different types of applications are there, and even robotic arm can be simulated. Okay, so and computations, we can use this software for student computations, and integration of AI and IoT is also possible, so that we are going to demonstrate in the sections. Okay, so next is that is we understood introduction of Webots, right? So now to use this software, first of all we should download the software and install it. Okay, so I'll show you how you can download in online. Okay, or with this link you can directly download the Webots, the specific version of the software which I am using. You can download directly from here. Okay, website also I'm showing you how you can download from website. You can go to Google. So there, go to Google and type Webots. So it is developed by Cyberbotics, you can see. So click on the Cyberbotics official website. Latest version is also that 2025, but the version which I am using, that is 2020 version, that is good for simulation, and because I am using that version. Okay, because advantage is there. So here there is a Windows version is there, Mac version is there. Okay, but here this version I don't want, so click on the down arrow and there is a older version option is available. So click on that and scroll down. That is second, go to second page. This one, 2020 revision 1. This version I'm using it. Okay, so this is a Windows version. So click on this. Software will be downloaded. Okay, see, when you click on this, it is downloading. It is 1.6 GB. Okay, since I'm already having it, so I'm just closing this one, cancelling this. So once you downloaded the software, its installation is very easy. Just double click on it and select multi-users and then go for complete installation. Okay, another way is you can click on the link which is given in the description box. Okay, this link will be given to you. Just click on this so that you don't have to search in the cyberbotics. And then there will be download option. So preview is not available. Okay, just click on download. Download anyway, and then it is downloading 1.6 GB. Okay, I'm already having it, just I'm closing it. So this is how you can download. So once you download, double click on it and select multi-users, then complete the installation. Okay, I hope you completed the installation. Once installation is completed, now I'm going to show you how to create the world in Webots. Okay, so after installation, go to Webots, open the application. Here I'm going to show you how you can create and then save your project. It's already some project is already existed, but I want to create new one. So go to File, New World, stop the simulation, and this is a reset simulation. So whenever you open the new world, it will be like this. Okay, so now go to Visits, because we want to create a project in this world. So go to Visits, New Project Directory, click on Next. So this is where it is storing C drive, users, iRobo automation, documents. If you want, you can change it to different location also. That is, choose the option is there. So there you can change the directory. Right now this is okay for me. So I'm doing 49 project. It's okay. So click on Next. And here don't forget to tick on rectangular arena. It's very important. Add a rectangular arena. Click on that, select all the things, click on Next, click on Finish. Okay, so even floor color we can change, floor for appearance we can change. So that also I'm going to discuss now. Okay, so this is a area where we are going to use, means our robot is going to use this area. So this area by default, say for example, go to floor size, it is 1 meter by 1 meter. Okay, units are meters. In Webots, all the units are in meters. Okay, if you want, we can increase the size. If robots are big, we can go for large size space. Okay, floor color, we can go to the appearance. It is checked is there by default. We can go for light strip. This is also possible. Okay, and different types of textures are there. Dark step. Okay, in this case right now it is okay. This is okay for me. So this is the floor adjustments. And wall thickness, if you want to increase, for example robot is very big, this wall height is very small, so in that case we can go for floor. There's a tile size, sorry, this one, yeah, this is a wall height. Right now 0.1 meter is there. We can go for 0.5, see here. So this is a large size, we can take 0.2. Okay, so like this we can do customization. So now we have created the project. Okay, and when you save, your work will be saved in the project directory that is already discussed, right? See, it is also showing here. See, in the C drive, this is the directory, 49 projects. So there your world is created. Okay, now so this is how we can create and save it. So click on save, so that your wall height is whatever changes you made, that will be saved. Okay, so for me wall height right now it is okay, 0.1. Okay, so now I want to change, say for example floor, I want to add the iRobo automation logo. Okay, so what I'll do is I will take one base node. In the base node I'm taking one shape, and in the shape, in the geometry, double click on the geometry, there is a plane, add, and in the appearance, double click, go click on the appearance, then click on add. So here texture is there, right? Texture right now null is there. So double click on the texture, add the image texture. So there in the URL you have to type the location where your logo is saved. So in my case iRobo logo is there. So in the location, or this logo, I'm going to copy this, and where our project are stored, for example go to C drive, users, iRobo automation, then one minute, we go into the location where, okay, iRobo automation documents, my project, documents, my project 49, create a project, sorry, create a folder called texture, and save the logo or the picture you wanted on the floor. Generally space is avoided, so I'm using underscore here. Okay, so right now this is a location. I'm going to copy this location and paste it in the URL, select, and now go to texture folder, select the logo, it is added. Okay, and now go to material, null, select material, add material. Okay, so right now logo is there, but to see the to improve the visibility of the logo, I'll go to rectangular arena there. So by default it is checkbox are there, so I'm going to change it to light strip. Okay, and come to the appearance. See, this is what the floor has got iRobo automation logo. So like this customization it is possible. And now whenever you are doing the work, this is very important here. Very important. Whenever you are doing modification or whenever you are working on the Webots, the simulation should be 0. Okay, if it is running, your work cannot be saved. This is very important. Okay, if simulation is running, okay, first of all save it. If simulation is running, in this time whatever your work you are doing, you cannot save. See, for example, if I try to save, it will indicate simulation is running, you cannot save your work. If you're still saving, then it is going to disturb the work. Okay, that is why. So don't start your work when simulation is running. So first stop it and then make sure that it is the 00 is there. Okay, so how to make it 00 simulation time? So here reset simulation is there. Click on reset simulation. So this is a reset simulation. Okay, fine. So now we understood how we can change the floor, color, texture, and the image you want, you can add it here. Okay, so and then how you can continuously save your work. Okay, fine. So after this we'll go into the next section. This is how we can create a new world, and you can create a new project folder, and you can save your work. You can change your floor customization, you can do it. Okay, and now we'll go to the next section, that is design of two-wheel differential drive robot. So for this, these are the when we want to design the robot, so we need some design parameters. Okay, that means what is the body dimensions, wheel radius, wheel thickness, what is the wheel position, all these things are required. Okay, so here robot body is there. The robot body is of you can say cuboid. That means height, width, length all are the same dimensions, that is 0.08 meters. That is one important point. Okay, that is the body dimensions. And then wheel dimensions, wheel radius is 0.035 meters. Okay, that is the radius of the wheel. And the robot body should not touch on the floor. There should be some ground clearance. That ground clearance is 0.002 meters. Okay, you can say around okay, so this is the one. And wheel thickness is 0.02 meters. And some sensors also we are going to use. So this is called the two eyes, you can say. See, the sensor positions from the center, from the body center is 0.07 meters. Okay, and then that is actually yeah, this is no, from the center we can say it is less than 0.04. so here some changes to be done. So here the position from this vertical axis, that is 0.02 meter. Okay, so this is 0.07 from the bottom, you can say, that is the position. So these are the dimensions of the robot we are going to design. So based upon the design, I'm going to design the robot in the Webots. Okay. So what we'll do it is we'll remove this customization right now. Once we design the robot, we can again switch over to this customization floor. Okay. So what I'll do is I'm going to, because clearly we want to see the robot base and everything, that is why. Do one thing, we'll try this floor settings. Okay. So first of all, simulation should be in stop mode condition and all are showing 0, 0. So this is the ideal condition to start your project. Okay. Now, first thing is go to the rectangular arena. Okay, click on this and then plus symbol is there. Then go to base nodes, because proton nodes means ready robots are there, but we are not interested in this right now. We'll take a base nodes because we are going to design the robot. So take a robot base node. Okay. Robot base node I've taken and expand it. In the children, first we'll take the transform node. Okay, so that means go to children here, take plus sign, and here we have to take the first transform, add. Why transform we will understand. Okay, transform means we can move the body in X, Y, Z direction. Okay, I'll tell you why it is. So under the transform, first of all, you should take the transform node. Under that, there is a children. So again, click on the plus symbol. So there you should take shape. Okay. Expand the shape. Click on the geometry. So first of all, we are designing the cuboid. Okay. So for that, you should take box, add. So by default, the box size is 0.1 meter, 0.1, 0.1 is there. Okay, that is 0.1 meter is there. So in our case, like as per the design, height, width and breadth, everything is in 0.08 meter. Okay, so this one 0.08, 0.08, 0.08. So in Webots, whenever we create the shape, that means it is created in the center of the axis. Okay, that means half portion below the floor, half portion above the floor. Okay, so that is important. So the 0.08 you are given, but half of the cuboid is below the floor. Okay, so that is why we need a transform node to lift the box, because half of it is below the floor. So we need, for lifting purpose, we need a transform node. Okay, so and what we'll do is, for example, you can go for appearance here. So there, go to PBR appearance, select on PBR appearance. I'll repeat again. For example, double click on the appearance, select PBR appearance, then click on add. There base color is there, so I want it in blue body. So red I will make it 0, green I will make it 0, enter. So blue body is there, and roughness you increase by 1, metalness remove it so that you will get a complete blue body. Okay, so this is about appearance, but as I mentioned earlier, half of the body is below the floor. See here, below the floor, half of the body is there. So that is why what you have to do, what you have to do is, like, transform node is there, right? In the transform node, under the translation is there. So there we need to lift the box in vertical direction. See here, XYZ, that is in Y direction means it is a green color. How do we know? For example, go to view and optional rendering is there, then show coordinate systems. Here you can see red color is X, green color is Y, blue color is Z. So we need to move in Y direction so that complete body is above the floor. So what is the total dimension? 0.08 meter is the total dimension, that is height. So half of the box is below the floor, so that is why we need to rise by 0.04, that is half of the 0.08. Okay, but here this is exactly touching the floor. 0.04 is exactly half of 0.08 but touching the floor. So what happens? It cannot move, so there will be a friction. It resists the movement, right? So that is why ground clearance is important. So ground clearance is already mentioned here, that is 0.002 meter. So that is why we are going to add 0.042. See here. So now the robot is lifted upwards and there is a gap. Okay, air gap is there. So it is ideal condition for movement. That is called ground clearance. So first of all, what we did actually, we taken the transform node, and under that we taken the shape node. Under the shape node we created the cuboid of height 0.08, but in Webots half of the body will be under the floor, so that is why we have raised it. Using the transform node we have raised it to 0.042, that means with a ground clearance also. So this is the body. So now this body I will name it so that I can use it for the bonding objects. We can use it. Okay, so that means I'm going to name it as a body. Okay, so and here bounding object, we should add bounding object so that it is a collidable object. It becomes a collidable object. So go to use body, then add. Physics means simple physics. Double click on the physics. So physics node allows to specify physical property like density, mass, friction, and also it becomes a real object. Okay, so add physics. So now the body is completed. Okay, so in the robot, the body is a part of children. That means body is a part of robot. Okay, so now we have designed successfully the body, and again you go to the click on the body and click on plus mark, because now we are going to add the wheels. So click on the base nodes. So here hinge joint is there. So there is a hinge joint is used between the wheel and the body. So click on add, then click on the joint parameters, double click, then click on add joint parameters, then click on device, double click on device. So we are going to take a motor, add motor, expand motor. So there is a name, motor name, so motor _1. Okay, so that means motor name, if we call it as a device or motor, the name of the motor is motor _1. So in Python code or in the C code, the name of the motor is very important, because in the program whatever name we are using it, so it should be same as the device address or motor address. Okay, now device is done. Now go to the end point, because we need to create a wheel now. So for that, first we'll take a solid node. That means double click on the end point, base. So there is a solid, add. Okay, in the solid there is a children, so double click, base, there is a shape. Okay, so expand the shape. So here in the geometry, double click on it, and wheel is a cylindrical shape, so we'll take cylinder, add, expand this, expand this geometry cylinder. Okay, so there by default the height of the wheel is 0.1 meter is there. Okay, so what is the radius and what is the height? Height is 0.02 and radius is 0.035. So height I'm going to do 0.02. Okay, and radius 0.035. So that is small compared to the body, that is why it is inside the body. Right now it is not visible, wheel is not visible. Okay, it's okay. We need to change the position of the wheel so that it is visible. Now go to appearance, double click. Okay, first of all we'll make it the position change. For example, we'll go to the translation here under the endpoint. Okay, so where we want the wheel actually? See, we want wheel that is, see what is the width of this cuboid? That is also 0.08. So half of it is 0.04, right? So here point in next direction 0.04. See here it is available. You can see the wheel. So it is in white color. So floor is also white color. So what I'll do, first I'll change the appearance here. I'll go to appearance, then add PBR appearance, add their base color. I wanted the red wheel, so let it be one red. Green I will make it 0. Blue I'll make it 0. Okay, and roughness I'll add it 1, and metalness 0. Okay, now I'll go to the again translation, because wheel position is not proper. Wheel is exactly on the floor, right? Now actually, say for example, I'll go to the rotation here. Right now it is, wheel is in flat condition. I want it in vertical condition. So I'll make it y0, z1. 90 degree rotation is required. 1.57 radians, it is, unit is radians. 1.57 radians means 90 degree. So 90 degree it is rotated. You can see here again, wheel, half of the wheel is below the floor, half of the wheel above the floor. Okay, so that is why, what is the wheel radius? 0.035, right? So we should go to the translation here. So here we need to raise the wheel, so it touches the, it should touch the floor actually, right? Wheel should touch the floor. So 0.035, that is the radius of the wheel. See here, it is clearly now visible. So the wheel position in x direction is 0.04 and y direction 0.035, so that wheel touches the floor. So this is what now wheel is created. Okay, and color is also selected, dimension is also there. But now there is another parameter called, in the, go to joint parameters. See, whatever coordinates are there here in the translation of the solid body, that is 0.04, x direction 0.035, this should be same in the anchor position, otherwise it behaves differently. Okay, so 0.04 and 0.035, it should be same in the anchor position, in the, that is the joint parameters. Okay, now we'll name this shape as wheel so that we can reuse it again. We have named this shape as a wheel. So now wheel, for wheel also bounding object should be added so that it is collidable and it is a real object, it becomes real object. So double click on the bounding object, select wheel, add, double click on physics, add. Okay, so this is for one wheel. The second wheel also should have the same physics, so that is why I will name this physics so that I can use it. So here wheel underscore physics. So I have named the, see, click on the physics and name it wheel physics so that I can use it for second wheel also. So both wheels should have the same physics. That is a concept. So we created one wheel completely. So we added bounding objects also, physics also added, and then anchor position is also added. Okay, now it's completely ready. So that is actually about one wheel. Okay, so now click on the hinge joint, add plus mark. So instead of okay, we should take the base nodes and again hinge joint, sorry, hinge joint, this one hinge joint, add, expand, double click on joint parameters, add, device, double click on device, rotational motor, and expand the rotational motor, the name in the name, so type motor underscore 2, that is a motor name. Okay, and now double click on the end point, there take a solid node, under solid node again children is there, so click on plus mark. So instead of creating from beginning shape and dimension everything, already wheel is saved. Okay, so wheel shape is already saved, we can directly use it. So add. So now second wheel is also added, but right now it is not visible because position of the wheel is not proper, because it's showing 0 0. So go to translation here. So now where we want another wheel, we want another wheel opposite to the wheel 1, right? So that means negative, that is minus 0.04. Okay, means the rotation means actually the second wheel is flat, it is on the floor, means horizontally. I want it vertically, so make it y0, make it z1, and 90 degree we have to rotate, so 1.57. If we change the view, it is, say right now again the half of the wheel is below the ground. So for that go to translation, then what is the wheel radius? 0.035. Okay, so it becomes, now the wheel, second wheel is also touching the floor. So we will rotate this. So this is a front view. Okay, now the second wheel is also ready, but whatever coordinates are there, wheel coordinates are there, same thing should be in the anchor position. Go to anchor, that is minus 0.04 and 0.035. okay, that should be same, see here. And now for the second wheel is also, go to bounding object, go to use wheel, select wheel, add, and double click on the physics. So there wheel physics is there, so that you should select, don't select the physics, so you should select wheel physics, so that both wheels will have the same physics. Add. Okay, and don't forget to save your work. Okay, keep on save your work. So now the second wheel is also ready. Okay, so everything is good. Okay, so that means in the robot, in the children, we have created body, we created wheel 1, that is hinge joint 1, and hinge joint, another hinge joint for second wheel. So body and 2 wheels are ready. Okay. Now what we'll do, like we'll add we can say 2 eyes so that we can recognize that that is a front of the robot, and we can also use sensors. Okay, so that becomes intelligent robot. You can say, for example, obstacle avoidance. So right now there is nothing. Okay, this robot is completely without sensors, means there is no intelligence here. Okay, so that means it is going to hit the objects. So for now, to create the eyes, okay, so for that again click on the hinge joint and plus symbol is there. So take a solid node, in the solid node expand it, and in the children again click on plus mark, and you can take shape. Okay, expand the shape, go to geometry, again I'm going to take box here, see here that is the size of the, by default is 0.1 meter, that is very large size. So we can go for 0.02, 0.02, 0.02. So it's very small, it is not visible right now because the position of the box is center, so it's very small, it's not visible. Okay, so first add the colors, click on the appearance, then PBR appearance, then expand it. Color, I want it in red color, so green I will make it 0, blue I will make it 0. Okay, then metalness I will remove it 0, roughness I will add it by 1. But the solid, that solid coordinates it is in the center, 0, 0, 0 means it is center, so that is why it is not visible. I will make it 0.07. Okay, and in X total distance is 0.04. I will make it 0.3. Sorry, this is 0.03. Okay, but in Z direction it should be in the front side of the robot. Front side from the center, the distance from the center to front face is 0.04. Okay, but the thickness is also there, so that is why 0.04 1 I'll add it. So it is quite big actually. So for that, what we'll do, let us make 0.01, 0.01 and 0.01. This is fine. Okay, and these are the translation. Okay, but now in the rotation, okay, let it be like this. Now right now it is okay. So now it is like eye for the robot, it is created, and X is actually quite more. You can take 0.25. Yeah, this is perfect. So X is 0.025, Y is 0.07, and Z is 0.041 is there. That is exactly on the face. You can also take 0.04 also, but this is not visible. It's okay, fine. This is okay. These are the coordinates. Now that is first eye, and the second eye Also same procedure. Click on the solid, click on the plus, and then take a solid node. In children, click on plus, shape, then double click on geometry, box, expand it, size is 0.01, 0.01, 0.01, and appearance, double click on the appearance, PBR appearance, add. Again, the color is required is red, so I will make it green 0, blue 0, and roughness add it by 1, and metalness to 0. Sorry, this is 0. And right now this second high is not visible because coordinates are at the center. So this is x, I want it in the other side, so that is minus 0.025, and this is 0.07, and this is 0.04 because front side. Okay, so now both eyes are visible. So for this, bounding object is not required. Okay, so let it be as it is. So this is how we can build a robot. We have built the robot here. So this is how it looks like. So now we'll quickly first and also save the keep on press the save button. So your work is saved here. Now you can see in the right side that is text editor is empty. That means now robot is there, but we cannot run it because there is no controller. Here text editor is there itself is a program. Okay. So now in the next section we'll see how we can add the controller as a text editor, and for demonstration what I'll do, I'll already program is ready, I will dump it and then run it. Okay, so that our designed robot is okay or not. Okay, so just cross check the anchor position, everything is added. So quickly I'll add the controller. So how to add the controller? Go to wizards, there is a new robot controller is there. Click on next. See here there are 5 programming languages are there: C, C++, Java, Python, MATLAB. So right now I'm going to demonstrate using Python. So click on next. So by default my controller is there. You can also change this. Okay, for example my controller sample, click on next, finish. So by default it is giving you the template how the program should be. So this is a by default text is there. Okay, so quickly what I'll do, I'm going to show you how we can run this robot. Now I'm going to, this is a code. Okay, this is a Python code is there. We are going to use motor 1, motor 2 in the code. We are going to call it, and we are setting the velocity here. This how to write the code I'll explain it in the next section. This is the demonstration. See, we have designed the robot. We're checking whether it is working or not. Before writing the code, we need to set up the Python also. Python installation is there. We need to add the path of the robot installation file so that it is going to work. Okay, so this is just a demonstration. There is a code here. See, what is the controller name? My controller sample. Okay, so in the left hand side in the scene tree, see here there is a controller. In controller by default void means nothing is linked, no controller is there, so that even if you start play this, so nothing is going to move because controller is not linked. Stop, reset. See here, stop, reset. Okay, so now go to controller, select option. So what is your controller name? My controller sample. Select it. Okay. So we have linked the controller, and after linking the controller, press save button. Okay. Now this is a code, and code also should be saved. And then go to run. Right now there is a simple code which moves the robot. The robot will move forward direction continuously. Reset. So it is moving forward. Simply it moves forward and it collides with the wall. I'll repeat again. Run. So your robot is stable, it is okay, it is moving. That is what we have checked it here. In the next section, I'm going to explain how to link the Python installation file to the Webots path. Okay, so what are the settings, pre-settings are required, and then how to develop this code, what are the functions are used, what are the syntax, how we can call the motors in the Python code. So all these things we are going to discuss in the next section. Now we have designed the two-wheel differential drive robot, right? So we have just designed it, and now it is time to write the code. So in Python. So first of all, you should download the Python, that is compatible version is 3.8. So here is the link. Even this link will be available in the description box. You just click on the link. Okay, and your downloads will means you will get the download. So Python 3.8. So go to folder, then double click on it. In my case, it's already installed. Whenever whenever you're installing, click on the path. Okay, so that is very much important. That is going to create the correct path so that Webots will be linked to the Python 3.8. Okay, so when you're installing, select the path. Okay, after that go for, it's a very simple installation. Python 3.8 will be installed to you. So that's it. Okay, so once it is installed, there is a once it is installed, once it is installed, make sure that go to tools, preferences, it should be Python command should be Python. That's it. So make sure that this procedure is followed, and now we can write the code. Okay, so here in the controller, see, first of all, we are Webots, it's not only for robots. Even for example, what I'm telling is like even generic applications, for example, school, park, or children's are playing like that. Animation also can be created. This is a generic software not dedicated to only robots, but robots also can be simulated. Okay, right. So what I meant to say is, first of all, you should call for the robot library. That is what my that is what the meaning is. So in Python, first import the robot library. Okay, this is a line 1. So you have to import the library, robot library. That is a first point. So this line means like it is going to import the robot class from the Webots control library, which provides the interface to control the robot in the simulation. That's the meaning of line number 1. Okay, if you want, say if you want to comment something, so you can use hash, and you can tell a message that this line number 1 imports robot library. Okay, that is a comment. It is considered as comment. Okay. Next, when we import the robot, now next is robot equal to robot function. Okay, so that means this is going to create an instance of the robot class. This object represents robot in the Vbot simulation. Okay, that is the meaning of line number 2. Next is there is a timestamp. Time step is nothing but it is for how much time you want the change in simulation. It is generally 64 milliseconds. I can just write 64 milliseconds. It is integer value. Otherwise, generic is say integer. Okay, robot dot get basic. Here camel case letters are followed. Time step, it's a function. Okay, otherwise if you just write 64 also it's okay. That's 64 milliseconds. For every 64 milliseconds it is going to change the simulation. That is a value. Okay, that means get the basic time step of the simulation in milliseconds and stores in the value, that is variable called time and time underscore step. This value determines how often the controller updates. Okay, next is we are going to define max speed. That is a variable. Max speed is 6.20. That means it is going to define the maximum angular speed of the robot's wheel, motors. It is in radians per second. What is the unit? Radians per second. Maximum speed is 6.20. Next is we are going to assign means what is how many motors we are used in the design. Actually there are 2 wheels, means 2 motors are there. What are the name of the motor? You can go to device, here motor 1. Name of the motor is motor underscore 1. So like that, motor 2, that is wheel 2, you go to device motor underscore 2. Correct. So first of all we should assign the motors to a particular variable. We call it as assigning the motor to a particular variable. Okay, so now we are going to define the variable called left underscore motor. Okay, so how to assign this left motor? So that is a function is there. That means robot dot, again camel case, get motor. Okay, and double quote, there you have to write exactly what it is in the scene tree. Exactly it should match, name should match, otherwise you will get error. Okay, so left motor is equal to robot dot get motor double quote motor underscore 1. So this is the syntax. So we are assigning the left motor variable to motor 1. Okay, so like that, right motor, so robot dot get motor underscore 2. Okay, this is syntax. This is a function we have to use. So we have defined 2 variables, left motor and right motor, and assigned the motor 1 and motor 2. Right? Now we have to define whether we are using velocity control or position control. Velocity control means keeping position infinity, so that by varying velocity, we can control the robot, for example, left, right, forward or backward direction. So we can control, right? So there is another control called position control. Position control means we are making velocity constant and we are changing the position. That is called position control. So in this program we are using velocity control. Okay, so velocity control means, say for example, left motor dot set position, again camel case, set position to infinity, but the variable we use is, variable type is float, single quote, INF is infinity, okay. Left underscore motor is a variable, right? So left motor dot set position, and it is to infinity, so that means velocity control. You can also comment it. So by setting position infinity means it is called velocity control. It is called velocity control. Okay, it's called velocity control. Now right motor dot set position, okay, variable type is float, again right motor also, left motor and right motor both are set to infinity. That is called velocity control. Next is, see, now it is a velocity control. Now we are going to use a while loop, okay, to continuously feed the left motor and right motor variable the speed value. Maximum speed is 6.20. okay. The concept is, if both motors are positive, it moves forward. If both, means velocity, velocity is a vector quantity, right? If both are positive, it's forward, both are negative, it is backward. One is positive, one is negative, means it spins around left or right direction. Okay, this is what we are doing. Now I am using while loop here. That means continuously it should move. So that is why we are using while loop here. Robot dot step time step, and okay, so that means until you press stop, this will be repeated. Okay, see, up to line 10 it is one time, that is we call it as the initialization of the program, but while loop is continuously repeated. So left motor dot set velocity, again camel case, set velocity. So what is the maximum speed? There is a maximum speed variable. Okay, and in the same way, right motor dot set velocity maximum max speed. Okay, so while loop means continuously it is repeated. So continuously it is feeding the data, means feeding the maximum speed value to left motor and right motor. Since both both are positive, it should move forward. So there are 13 lines in this program. So line by line I have explained to you. Okay, so let us see whether it is working or not. First of all, whenever you edit the program, you should save it. Save. And then make sure that simulation in 0 condition. So it is reset condition. See, this is a reset condition. And now if you press run, it should run. See, it is processing the program, that is my controller sample.py. So there are some errors here. What is that error? In line number 2 there is error. What is this error? We'll see that. Maximum speed we have defined. Indentation is there. Okay, that is a problem. We'll give some space. Stop it. See, stop the simulation, then reset, save, and run. Stop, reset, run. So here some, yeah, this is time step. It's moving. I will repeat again. Stop, reset, zoom out using the mouse wheel, then run. See, it is executing your program. It is simply moving forward because both are positive value. And it is of little bit high speed because maximum speed it is moving, right? So again, stop, reset. So the program we are executing now is this one: continuous forward, backward, spin left, spin right, turning left, turning right. This is what we want to achieve, right? So now how to move the robot backward? So for that I will make a minus here. Both left motor and right motor both are negative. Velocity is a vector quantity, right? So I'm changing the direction here and save it. Save the program and then run. It's moving backward. Okay. Again, stop, reset. So this is how we can achieve the backward motion. And next thing is I want to turn left or right. Okay. So for that, this is the concept. See here, left speed and right speed. How to achieve? Sorry, left or right. Left turn means if left wheel speed is less, right wheel speed is high, then what happens? It will take the left turn. Okay, like that. If right speed is low, means value is less, left speed is high, then it will take the right turn. Okay, that is a one thing concept. And another thing is value is same, but one wheel is negative, one wheel is positive, then spins around the left or right direction. That is called spinning. Now I'll demonstrate. Now I will make it one wheel positive, left wheel is positive, right wheel is negative. So first save it, then run. Okay, it spins around the left, sorry, it spins around right according to me. Okay, stop. Now left wheel is negative, right wheel is positive, so it should spin around left. It's not updated because see, you can observe that after changing and directly running the program, so that is why it's not updated. First you have to save this and make sure that simulation in reset condition, and now start. It is spinning around left direction. Okay, now if you want to make a turn, then for example, if you want to take left turn, so left wheel should have lower velocity. So for that, for example, 0.25 means 25% of maximum speed. Okay, only 25% of maximum speed is at the left side motor. Right side motor, full speed is there. Okay, and then save it, then run. See, it is turning left, but with a radius. Some radius is there. Curvature is there, or curve is there. So this is what depends upon the speed, magnitude. Okay, if you still reduce 15%, stop, reset, run. That means a radius, turn radius will be less. Okay. Like that, if you want to turn right, so then what I'll do, 0.25% means 25% to the right motor. The speed is only 25% percentage of maximum speed. Left motor is full speed. Then it should turn right. Okay, this is how we can control forward, backward, spin left, spin right, then left turn, right turn. This is how we can achieve. Okay. So this is a summary here. So velocity control mode. Okay. So if both wheels are positive, it moves continuously forward. Okay. All speeds are negative means backward. Left wheel is positive, right wheel is negative. That means spins around in the left direction. Okay. Next again, left speed is negative, right speed is positive. Then counterclockwise rotation. Okay. So this is what we have discussed. Okay. So this is about the project number 1. Okay. So next is project number 2, that is position control. In the next program, we are going to demonstrate how we can achieve position control. Position control means we are not setting the position to infinity. It is having some value. So that is called position control. Okay. So next thing is, say for example, robot should move 0.2 meter, some distance. Okay. And it should stop. Not continuously, infinitely, it should not move. It should move only to a particular distance and then it should stop. Say for example, it should move forward by 0.2 meter and backward by 0.2 meter. Okay. So let us program this position control. Okay. So go to the Webots. And here some of the lines we can retain it. Already I given the explanation. So some of the lines we can retain it and continue. Okay. So that is first line which imports the robot library. Okay. From to the controller so that your program will run. Okay. That which creates a robot instance. Second line. and time step is nothing but 64 milliseconds, right? And that is integer value. And next is maximum speed is 6.20, that is as it is. Okay, and so here the maximum speed, if you define 6.20, that means that it always that is called a velocity control, right? So what we'll do it is here, that means okay, so let us do this much from the beginning. Okay, so now after time step, so it is like we'll take one variable called wheel radius. What is the wheel radius? See, you go to the scene tree here. Wheel radius is inside the wheel shape geometry. Wheel radius is 0.035. So here you should enter that value. 0.035. That defines the radius of the wheel. Okay. This value is required to control how many rotations required. Now the question is, see, we are required the movement of point to meter. Okay. So this program, you can say in the beginning you can add a comment. So robot should move 0.2 meters, say forward. Okay, that is our output, required output. Next is the target position we need to define. Okay, so that means target position or distance, you can say. So that is 0.2 meters. Next is the robot will move. See, now it is important to calculate how many rotations required to cover 0.2 meters with a wheel radius of 0.035 meters, right? So for this we can have one formula for this, right? We can say fine. Now here fixed speed, that means we are taking one variable called fixed speed, and that is 3.0. This can be maximum speed also, that is 6.20 also possible, right? Sets the rotational speed of the wheels in radians per second. Radians per second, the unit is, that is 3 radians per second. That is a fixed speed. At that particular speed, now see, this is called position control, okay, where velocity is fixed, position is changing, right? So velocity is fixed, that is why the fixed speed variable, that is equal to 3. It can be 6.20 also, that is maximum. Okay, next line is, we'll take a variable that is left motor is equal to, that means we are assigning the motor 1 to left motor variable. Okay, this is a declaration, means assigning motors to variables. Now right motor is equal to robot dot get motor, that is camel case motor underscore 2, right? Now motor 1, motor 2 must exactly match the motor names, and that is already we discussed, right? So that means as per the scene tree we should label exactly the name of the motor, right? Next thing is like wheel rotation, that is a variable, or wheel rotation. We need to calculate number of wheel rotation is equal to what is the variable here? Target distance. Okay, so I'm going to target distance divided by wheel radius. So this is what the formula. Wheel rotation variable is equal to, that means number of rotation is equal to target distance divided by wheel radius. So that means how much wheel must rotate in radians to move the desired distance. That is a formula. Okay. Next is we need the see, we have calculated the wheel rotation, so now we should assign this wheel number of rotation to a left motor and right motor. Okay, so that is why left motor dot set position, it's a camel case, left motor dot set position, that is wheel rotation, right, like that. Right motor dot set position, again wheel rotation. So now we are defining the position, that is number of rotations we are defining to the left motor and right motor. Okay, position we decided, but now it should move continuously till the target, right? So that is why we have to now set the velocity. So left motor dot set velocity, camel case, set velocity to what is a fixed speed. So this is a variable fixed speed. Okay, in the same way, right motor dot set velocity that is fixed speed. Okay, these are all like initialization. Okay, so next thing is there is a while loop, because it should move continuously, right? There is a time step. Next thing is, since there is nothing to write here, so we just pass, you can give it, there is nothing to write. Now let us save this and try to run it. Actually it should move forward. There is some errors are there, so that is why it is running previous program. So here see line number 13, instead of wheel, so spelling mistake is there. Save it, reset, run. it is moving and it has stopped after reaching 0.2 meter. Okay, again stop, reset. Say for example, if I make 0.4 meter, then run, it means first save the program, then run. It will move 0.4 meters. Okay, let it be 0.2. Now assume that it should move backward. So what is your opinion to change the program? Which line we should change? Velocity. Okay, velocity is fixed, right? So now just answer me where we should change. We can try this. Say for example, distance we have calculated, that is 0.2 meter only, right? So by changing the negative velocity, save, run. Now it is moving forward. Because it's a fixed velocity. Now wheel rotation, see, wheel rotation to be negative value, so that robot will move backward. Both are negative, so that it will move backward. Exactly the distance is 0.2 meter. So we have discussed the project number 2, that is position control, move forward and backward by 0.2 meter. Okay, in the next section, we are going to discuss how we can use the keyboard keys to control the robot, that is forward, backward, left, right, by using the computer keyboard keys. Okay, so let us develop the program for arrow key controlled. That means we are going to use keyboard keys to control the differential drive robot. Okay, the required output is by pressing up key, it should move forward, down key, then backward, left key means left turn, then right key means right turn. Okay, this is what required. So let us go to the Webots. So here some of the lines we can keep it. So this program is not, this is a control of robot using keyboard keys. Okay, so the line number 2, that is importing the robot library. Okay, so line number 4 is creating the robot object, and time step is nothing but 64 milliseconds. So that is the one, and this portion from here we'll start. So these three are common for all, means most of the programs, right? Fine. Next is like we'll use the maximum speed, that is max speed. Max speed is equal to 6.20. Okay, so that defines the maximum speed, that is radians per second. And next thing is we should enable the keyboard. Okay, so that is, it is a comment. So enable keyboard, that is the function we should use, that is keyboard is equal to keyboard function. Okay, that means that creates a keyboard object to read the key presses. Next thing is, so keyboard dot enable entire time step. That means for every 64 milliseconds, it is going to update the keyboard functions, right? That means activates keyboard input for every 64 milliseconds, it is going to read. Next is initializing the motor. Initializing the motor. This is also common for every program, right? That is, we are going to create a variable called left motor is equal to robot dot get motor, that is camel case, double quote, motor underscore 1, close the double quote. Then right motor is equal to robot dot get motor to. Okay, so we have assigned the motors to the variable called left motor and right motor. Now we are using here velocity control. So that is velocity control means what? Velocity control means we are defining the position as infinity, right? That is left motor dot set position, that is, it's a float value, type of the variable is float, infinity. Okay, then right motor dot set position, okay. So this is a velocity control, so we are making position to infinity, and initial position of the robot should be stopped, right? So that is why, so we have to set motor velocity, initial velocity should be 0, 0, like that. Right motor dot set velocity 0, 0. Okay, that means initial velocity is 0, means initially the robot is stopped. Okay, now we need to enable, see, user interface like should receive the information whether to press or not. For example, whether the program is ready, say for that. So we are using the print option. We can print some message to the user, that is arrow key control enabled. Okay, this is a message, you can print it and print what are the commands are allowed. Okay, say for example up, that is forward. Okay, next is down key, that is backward. Next is left key. that is left turn, right? Left key for, can also type for left turn. Some errors will be there, it's okay. Now right key, that is right turn, okay. And so it will be very long. What we'll do it is like, it does not type everything. It is okay. The thing is that forward, okay, backward, then left, right, and space, that is stop, you can say. So now we are, that is we are typing the main loop, okay, that is while loop. While robot dot step, that is time step, for every 64 milliseconds. It is going to check the key, okay. So that is key is equal to key, that is keyboard dot get key camel case function. That means continuously it is reading the keyboard keys. So it reads the currently pressed key, okay. If no key is pressed, then returns the value -1 and it stops, okay. Now if key double equal, okay, keyboard dot up, that means it should move forward, okay. So forward means what? That is left motor dot set velocity, that is max speed, okay. So that means both left and right motor both should be in positive magnitude so that it will move forward. Right motor to max speed, both are positive, so it moves forward, okay. Next it is else if, so that is else if key equal to keyboard dot down, okay. So here colon is missing. Else if So backward means what? Both are negative. So I'm going to copy this. I'll make it both are negative. Okay. And I'm going to copy this. Else if statements. If key is left, dot left, then what should happen? It should move left, right? So I'm going to copy this. Left means that is, we are going to see how when vehicle means robot will take the left turn, left wheel velocity value should be less, right? So I'll go to the left one. So I'll remove the negative. So left wheel, I'll make it low velocity, that is say 0.3 times the maximum speed. Okay. So in the same way, I'll copy this else if statements. That is right. So right means what? So again, we're going to copy this. So left motor, high maximum speed. Right motor, 30% of maximum speed. Okay. Next is the last one. That is, by pressing this space key, it should stop. So now else if there is a syntax, so that is, it will take the space ASCII value, okay, that is this function is nothing but ORD means ORD bracket of single quote means gets the ASCII value of the space character. Okay, so if space button is pressed, then it should stop, right? So I will make it both the wheel set velocity to 0. Stop means 0. Okay, this is the code. So let us, and here in the simulation you have to stop the simulation, reset it. Okay, save the code, save the program. Now let us run, check whether error is there or not. In the console you have to, so there are errors, that means line number 22, so what is the error? Keyboard, so here what is missing here? Okay, maybe this capital K. Error is expected indented block. Okay, we'll give some space. Now the line number 24, left motor set velocity. Okay. So after if there is an indentation is required, save it. Keyboard is not defined. The line number 8. That means we need to import the keyboard also, right? So that is missing. That is why the error. Keyboard is not defined. In line number 35, type error. What is error? Expected a character but string of length of 0 is found. Let us type space. Yes, now the program is correct. Okay. Now it is in the console, it is asking forward, backward, left, right, stop. For stop, space bar is used. So let us enter forward. Click on the console and then okay, and the thing is that we need to stop, reset, okay, and then run. Forward. Now I'm pressing the up key, so it's moving forward. Back key, space for stop, okay, forward, up key, space, stop, backward, down key, stop, left, then right, stop, forward, backward, stop. yeah, it's working. So this is the code. So this is how we can by seeing the console is going to help you where which line there is a problem, and so that we can fix the problem. Okay, so in the next problem is we are going to develop the code for obstacle avoidance robot. In this I'm going to show you how we can include the distance sensor. Okay, and so that we can use it in the program and get the output that is obstacle avoidance robot. Okay, now we are focusing on development of code for the obstacle avoidance robot by using two distance sensors. Okay, so first I'm going to demonstrate how we can add a distance sensor to our robot. Okay, so this is a Webot. So we have developed the robot, right? That is body, and then wheel 1, wheel 2, then 2 eyes are there, means we build this cuboid shape so that represents the eyes of the robot, but not actually, there is no sensor there. So that is why, so first go to the solids, expand it on the children, right click, or you can press on plus mark. So there in the base node, you should select the distance sensor. Okay, expand the distance sensor. You can observe here there is a white rays. White rays are there. So that means the sensing rays are not in front of the robot. Okay, it should be perpendicular to the front face. It is not there. If these rays are not visible to you, then go to view, optional rendering. There you should select the show distance sensor rays. Okay, if it is not visible to you. So right now it is visible to me. Okay, but it is not perpendicular to the front face. Okay, to change that, and before that, the sensor name is important. So by default it is distance sensor is there. So this is ds right to me. Okay, ds right. So that same name ds underscore right is the name which is used in the program. Okay, now rotation is not proper. Okay, so we need to rotate this rays 90 degree. Okay, so that is why go here minus 1.57. So it exactly perpendicular to the front face. Okay, this is what you should do. So what I've done is I've added a distance sensor to the child of the solenoid. Okay, so that I can have the distance sensor in the exactly the position of the object that it looks like high, right? Now again go to the second solenoid here. The second solenoid, go to children, plus mark. So take the distance sensor, expand. The name of the distance sensor is DES left. Okay, and the rotation, again see here, raise the left distance sensor, raise also not perpendicular to the front face. So go to rotation. So here 1.57, that is 90 degree. It should be minus so that it will come to the front face. So now both sensor rays are perpendicular to the front face. So okay, so you mean to say that is the sensor rays are facing, means that's okay, fine. Next, we have added successfully the sensors. Now it is time to write the code here. So as usual, we should call the library, that is robot library, to the controller, right? That is from controller import robot. And next is there is a time step that is equal to 64, that is integer value, that means 64 milliseconds, and threshold, that is sensor threshold, is 850. Actually maximum value is 1000. Okay. Next is there is a avoid duration. Avoid duration is nothing but number of control cycles, okay, required to avoid the obstacles. Next is creating the robot instance. Robot is equal to robot function, and then initializing the distance sensor, right? So now we are initializing the distance sensor. Distance sensors, so that is ds left is equal to robot dot get distance sensor, that is camel case distance sensor, that is ds left, that is name exactly should match in the scene tree. Okay. Now ds right robot dot get distance sensor, and here right ds right. Okay, and we should enable the distance sensor, so ds left dot enable time step, and that is ds right dot enable. Okay, so this is going to enable the sensors. Okay, and next is now we are initializing the motors. So motor underscore 1 robot dot get motor, that is what is the motor name in the scene tree, that is motor underscore 1. In the same way, motor underscore 2 get motor, that is motor address is motor 2, motor underscore 2. Now we are going for velocity control mode. So velocity control mode means we are setting the position infinity, right? So that is motor underscore 1 dot set velocity, so that is infinity, and in the same way motor 2 also. Okay. That means velocity control is there. Okay, next is we are initializing the motor speeds or speeds. So left speed, it's a variable, left speed is equal to 3.0, then right speed is equal to 3.0. Next is we are defining the obstacle avoidance counter. So that is avoid counter we are initializing to 0 initially. Okay. So next is that is main control loop, that is you can say while loop. We are using while loop now. Before while loop all other executed one time, but while loop is continuously executed repeated until you stop the simulation. Robot dot step, that is time step. Okay. Next thing is so here indentation also very much important. Okay, so the left value, so left value is a variable we are using to store the sensor data. ds left dot get value. In the same way we are also using the right value is equal to ds, that is distance sensor, that is right distance sensor, get value user. That means we are assigning the data of the sensor to variable that is left value and right value. Okay. Now if avoid counter greater than 0, that means it is going to input the value that is avoid counter, that is -1. Okay. So now say for example if the right value is less than threshold, so what happens, that is left speed equal to 3.0. that means, see, if right value is less than threshold means there is a right side there is obstacle, so we should turn left. Okay, so that is what we are doing it, right speed so that means it is turn right. Okay. Sorry, this is turn left. Okay, your indentation is very much important. Else if left sensor value is less than threshold, okay, so that is we need to turn right. So left speed is equal to -1.5 and right speed is equal to 3.0, that is turn right. So the concept is, if left sensor value is less than threshold value, that means left side there is obstacle, we should turn right to avoid the obstacle. Okay, and this is else statement. Else, so we are this one. If else, so that is default, it is forward movement, default forward movement. Forward motion, that is left speed is equal to 3.0, right speed is equal to 3.0. Okay, and next is if that means detect obstacle. So if left value less than threshold or right value less than threshold, next is avoid counter is equal to avoid duration. Next is apply motor speeds, that is motor underscore 1 dot set velocity, that is left speed, that is right speed. Okay, now first save the program, then save the robot also, because we've added the sensors, right? That time you have not saved the saved our work. Okay, now run. So there is some error here, that is line number 47. Yeah, here there should be indentation is required. Save the program, reset, run. We'll do one thing, we are going to clear the console and then run, so that we'll get the latest error. It is 10. So we'll go device rotation, maximum velocity is 10. Okay, joint the requested velocity infinity exceeds this one, we made a mistake here. Set position, right? Set position to infinity so that it becomes velocity control. Save the program, stop, reset, run. So it is turning. It avoided the obstacle. Obstacle is wall itself. Now it should turn. So this is how we can develop a program for obstacle avoidance robot. Now we are going to discuss how we can control the differential drive robot through voice commands. Okay, so for that we need to download and link it to the Python, this WASC voice recognition model. Okay, here link is given, so you can click on this link. It will be given in the description box. You can click on that link. It will take you to the voice recognition model. Okay, see here, WASC model. You are going to download now. So since I already downloaded and it is there, so I'll show you how you can create a path for this to the Python. Once you download it, so this is where you have downloaded. Now right click, extract. I think it is still downloading. Okay, so when extract the folder, and after that go to C drive. So there you can find the model. You have to copy paste the folder in the C drive. That's it. Okay, Oaks model, that is version 0.15. So this is what it should be placed in the C drive. Okay, so that is to be done. It is still downloading. See, it is visible here. It's okay. We'll go to the Webots. So here robot is same, so we're not changing anything. So in this robot there are two motors are there called motor underscore 1, motor underscore 2, and two sensors are there, that is DS left and DS right. Okay, now we are going to write the code in the controller. It's a Python controller, right? As usual, that is from controller import robot. Next is we have to import sound device as SD. Sound device, we need to import the sound device library. That means it is going to import sound device for microphone audio input. Next is we need to import Q. That is Q is used to safely pass audio data between the commands, okay, between the threads. So that is important. So import Q. And next is import JSON. So JSON is used to decode speech recognition results. Okay. Then after that, import time. That means time module is used for timeout handling. Okay. So that means if voice is not voice comments if not reached in time, so again it is going to start from the beginning like that. Okay, next is from host recognition model. So we need to import, that means entire folder is there in the folder we need to import model. Okay, then recognize. So this is the, for example, if you go to the C drive where this folder is there, if you open this and there is a configuration is there, so model is there. Okay, fine. So this is what you have to import was speech recognition classes. Okay, next thing is robot instance, robot function, and next is get the simulation basic time, that is already timestamp. Time step is equal to 64 milliseconds, right? And max speed .20 or 28, it can be 6.20. So now we need to assign the motors, right? That is left motor and initializing the motors. So that means left motor is equal to robot dot get motor. So motor names are small letter, that is motor _1. So we are going to copy this and right motor is equal to motor _2. Okay, in the same way now we need to switch over to, that is velocity mode, right? So velocity mode means we are setting the position to infinity. Velocity mode means what? That is left motor dot set position, that is it's a float value, single quote, infinity. Now it is right motor set position, again infinity. Next is like initialize the motor velocity to 0. That is left motor dot set velocity to 0. Now right motor, set velocity to 0. Now we can go for VOSC, that is voice recognition model setup. Okay. That means we need to define the path. Okay, so that means we need to set path to the offline VOSC model. See, in voice recognition there are two types. One is online and offline. Online means it is connected to Google voice commands, but what I tried, actually I tried that online voice commands, but it is not fast. Sometimes it is not recognizing the voice commands. That depends on internet and all, so that is why I am using offline mode. Okay, speech recognize. So path is, that is model underscore path. So model path is equal to, that is C drive that is VOSC model or you can copy paste the link. Okay, so this is the path, and next is load the VOSC model. So that is model is equal to model path. Okay, next is creating a recognizer with simple rate, that is 16 Hertz. So here create a recognizer with sample rate, that is 16 kilohertz. Okay, and limited grammar. So recognizer is equal to recognizer model, that is 16 kilohertz. Okay, grammar. Okay, next is, so create a queue. Create a queue to store incoming audio. Okay, that is audio underscore queue is equal to queue dot queue function. Okay. Next is audio callback function. Okay, that means called automatically by sound device. Define audio callback in data frames time info status. Okay, so indentation, that is, here you can say convert audio input to bytes and push into queue. So that is audio queue dot put bytes in data. Okay, now there is a voice state, that is current command state. See, because robot, it should not move initially. When you run, it should not move, right? So that means command equal to stop. Next is store the time when last command was received. That is last command underscore time is equal to time dot time. Next is, so for user interface we need to print some information, right? So that is print user instruction, that is print offline voice ready, that is forward commands are allowed, forward, backward, left, right, stop. So these are the commands are valid. Okay, so you are instructing user to speak out only these words. Next is audio stream. Okay, that means we are create a raw audio input, so that is create a raw audio input stream from microphone. Okay, that is stream is equal to, that is speech recognition device dot dot inputs stream so now some indentation is given, okay, that is sample rate is equal to, that is 16,000, okay. Next is block size is equal to 8,000, that is number of sizes, number of samples per audio block, okay, audio block. And data type that means audio data format, and channel, that is channels is equal to 1, and callback is equal to audio callback, that is function called on new audio data. It is close it. Next is start capturing microphone audio stream dot start function. Now we are running the main loop, that is main loop that is, you can say, run until Webots simulation stops. So that is while loop robot dot step time step okay, and now we need to process all available audio data, that is while not audio queue dot empty function indentation is important, so data is equal to audio underscore queue dot get function. Okay. Next is check if a complete speech phrase is detected. Okay. If recognizer dot accept wave form, that is data. Next is convert recognizer, convert recognition result from JSON string to dictionary. Okay, that is result. So here indentation is important. Result is equal to JSON dot load recognizer dot results or result function. Next is we need to extract. Okay, that is extract recognized text and convert to lowercase, that is text is equal to result dot get text dot lower function. Next is if any valid word is recognized, if text, okay, that is print heard. Correct, right? If valid input audio input is received, then we are going to print heard. Okay, and command is equal to text. By default command is equal to stop, but whenever valid is received, then we are reassigning command to text. Update the current command is right now stop, but whenever, for example, valid, for example, forward, backward and received, then it should be updated to the command. Last command time is equal to time dot time function. That means reset the timeout timer. Next is safety timeout. If time function last command time greater than 5, that means if command is equal to stop. Next is that is move forward. If command double equal to forward, then left motor set velocity .6 times the max speed. That means we are using 60% of the speed. Okay, this you can also change. Now it is a right motor set to same speed. See, both are positive, both are same speed. That means it should move forward. Next is moving backward. So what I'll do is so here indentation is important. Else if double equal to backward so I'm going to copy this portion. Okay, that is backward motion means both are negative, right? So I'm going to copy this. Here indentation is important. So now forward backward is okay. Now it is left. So left means left motor, okay, should be negative, right? And we are going to reduce the speed here so that it spins around the left direction. Now it is right. So right means go to right motor, then add a negative symbol. Okay, so it spins around in the left direction. Fine. Now the last one is stop. So this is the last statement, so I can use a else command. else left motor and right motor velocity is set to 0, that is stop. Okay, so that is a program. You can add a comment here also, that is stop robot, this one. And now save the program, save the robot also, then run. So there are errors are there, line 1. What is error? So there is an import spelling mistake is there. Save it, run. Indentation, that is line number 87. If text, okay, save, stop, run. So here line number 87, okay, we'll move this one, save, stop, reset. We'll do one thing, we'll go into wizards, tools, clear all console, then start from beginning. So there is a error. So line number 87, there is an indentation. And there is now new error is now, that is fixed, that is line number 94. What could be their indentation? Again, indentation error is there. So we'll go into tools, clear all console, then run the program. So here line number 94, otherwise we'll move this one. So we are going to clear all console. So we are stuck in line number 94. Next is line number 94 is okay. Now line number 121, this one. Right motor set velocity to 0. That is line number 32. Recognizer. Here capital K is missing. Grammar not defined. So here we missed one line, that is grammar we should add. Okay, so this was missing actually. Save it, reset, run. So that is line number 80. This is maybe spelling mistake. So now we can see in the console offline voice is ready. Okay, forward, so it is moving forward. Forward, stop, backward, stop, right, left, forward, backward. So this is the final code. So now all functions are working. So this is the final code. Okay. Now we are going to discuss a keyboard control plus there is a obstacle avoidance safety is also there. Earlier, maybe project number 3 or 4, we discussed like how we can control robot with keyboard functions, right? Keyboard keys. But in that, obstacle avoidance control was not there. That means if you keep on press forward, it goes forward. But if it finds obstacle, there is no turn left or right. Simply it is going to hit the obstacle. Okay. So now this program, what we are going to discuss now, that is keyboard function, keyboard control is also there. Plus additionally, there is a obstacle avoidance that is only in forward direction, because in the front of the robot there are two eyes, that means two distance sensor is there. So only in the forward direction it can provide the safety against the obstacle collisions. Okay, so let us open the Webots. So we have not changed the hardware, means design is same. Okay, only the program, even the controller is also same. Okay, so that is my controllers underscore sample, that is a controller name. So I'm going to just change the code so that the function is going to be different. Okay, I'll go to tools and then clear all consoles. Next thing is so we'll start from the beginning as usual. So that is from controller import robot, even keyboard is required, right? So keyboard is there. Next that is time step is equal to 64, that is 64 milliseconds. And then max speed 3.0, then sensor threshold, okay, that is 850. Next is robot installation, robot instance. So that is robot is equal to robot function, and that is keyboard initialization, can say, that is keyboard, that is keyboard function. Next is keyboard, we are enabling it, enable, that is for time step. That means for every 64 milliseconds it is going to update the keyboard keys status, it is going to update. Okay, next is distance sensor. That means allocation, that means there are two sensors, are the ds left and ds right. So we are assigning to a variable called again ds left, we are assigning to a ds left variable robot dot get distance sensor double quote, that is ds left. Okay, so I'm going to copy this, ds right, this also ds right. Okay, and next is ds left dot enable, that is time step. So I'm going to copy this, next is ds right, next is motors. So left motor is equal to robot dot get motor underscore 1. Right motor Right motor address is motor underscore 2. Next, left motor, so that is velocity control pins, set position to infinity, that is float, data type infinity. Right motor position also infinity, so that means you can say it is a velocity control. In velocity control, we'll make position infinity. So left speed is equal to 0, 0.0. That means right speed. That means initial value will be 0. That means robot will stop, because it is like when we press the control key, when we press the keyboard key, then only it should move forward or backward. So that is why we are setting initial velocity to 0. Okay. Next is, so print keyboard control with forward obstacle safety. Okay, so now actually we are starting the main function here, that is main loop, that is we are using while robot dot step, that is time step. Okay, so now we have to read the sensor data, right? So that is read sensor. So here indentation is important. So here left, that is left value, that means we are defining new variable, that is left value is nothing but the left sensor value. Next, right value is equal to, we are assigning to the right sensor, ds right dot get value. Okay, next is obstacle ahead, that's a variable we are assigning to, means if left value less than threshold or right less than threshold. Okay, so now key is equal to keyboard dot get key default stop will be there. So that is left speed is equal to 0, right speed is equal to 0. Next is there is a keyboard control. If keyboard dot up, okay, if not, obstacle ahead. Okay, the thing is that if keyboard up button is pressed and if not obstacle ahead, that means if obstacle is not there, then it should move forward, right? So left speed equal to max speed, right speed is equal to max speed. Else left speed so here indentation, that is here, if it should be aligned to if. Okay, and next is elif, means else if key double equal to keyboard dot down, that is left speed is equal to minus max speed, right speed is equal to minus max, because both are minus for backward movement. Okay, so next thing is I'll copy this section and next is left if left key is pressed, then it should turn left. That means left speed motor speed should be less, velocity should be less, that is 0.3 times 30% times the maximum speed. Okay, your indentation is important. This is right and left wheel maximum speed will be there and 0.3, that is 30% of maximum speed. Okay, you can add a comment if you want. This section is for forward, and if obstacle is there, it is stopped in forward actually. So in backward there is no need to control here because there are no sensors. So this is about right, and next thing is, so that is last one, else if that is, it is going to take the ASCII value ASCII value of the space bar. This is a syntax, we use it, and stop by pressing space bar, that is stop, that is 0, 0. And lastly, there is a apply speeds. So left motor dot set velocity to left speed, and right motor set velocity to right speed. Because see, in all these cases it is going to solve, and then finally it is set the speed. Okay, see here. And first thing is, first you have to save the code, then reset the robot, run, run. So there is one invalid syntax is there, errors are there, that is line number 1. So here it is not dot, it is comma, right? Save the program, stop the robot, reset, again run. So there is one more error, line number 53. Indentation error is there. We'll check this one. Okay, so now everything should be aligned to this one. One backspace is required. Save it, run. Now 71. What is error here? Set velocity. Indentation problem is there. Okay. Save it. Save, run. It's moving. There are no errors now. See, in the console we got the output, that is keyboard control with forward obstacle safety is there. That means it is ready. So now I'm pressing the up key. Okay, that is stop, reset, start. So it's moving. I'm zooming out. Okay, now say I'm pressing the up key. Robot is moving, but it should not collide with the wall because there's a safety. See, it is stopping. I'm keep on pressing the up key, but it's not moving forward. That is a obstacle avoidance program is also included in the keyboard control function. But in the back side, there is no sensors, so we cannot have a obstacle avoidance. So it is going to hit the wall. Okay, so forward, now left, right, forward, left, right. Okay, so this is a final code from here to here. Okay, we'll see in the next section, that is a voice control robot with obstacle avoidance. That is also there. We'll take up in the next section.